All right, welcome to Unit 11, which is all about gases. We've talked about reactions, and in this particular chapter, we're going to focus on the things that are in the gas phase. What do they do? How do they act? How temperature, pressure, volume, moles, all of those things relate to gases. And when we're talking about gases, we're going to focus on what's called the kinetic molecular theory. And the kinetic molecular theory, it basically explains properties of things. And if you think about what the word kinetic means, it means movement, right? So the kinetic molecular theory, and it says right here, describes the behavior of matter in terms of particles in motion. So in our study of gases, we're really going to focus on how the gases are moving on a molecular level and how that affects all the other properties and behaviors and things having to do with those gases. Now, the kinetic molecular theory has four basic parts to it. First, it says that gases consist of small particles separated by empty space. So when we talk about the volume of a gas, we're really talking about the space that the gas takes up, which is mostly empty space. The second part says gas particles are too far apart to experience significant attractive or repulsive forces. So because there's so much empty space between them, they really don't interact with each other very often. And if they do, they don't attract each other, they don't repel each other. They just, kind of pass by. They might collide every now and then, but most of the time they don't interact. Third, gas particles are in constant random motion. So the random part means they don't have a specific place they have to go. They can move in any direction, but they are going to be traveling in straight lines. If you look at the picture on the right, it kind of shows that constant random motion. And then the fourth part says that collisions between gas particles are elastic, which means that when one particle collides with something, there's no kinetic energy lost, that it transfers that energy completely. So those are the things we're going to be assuming about gases as we study their behavior in terms of how they're actually moving. Now, kinetic energy depends on two things. It depends on the mass of the particles, and it depends on how fast they're moving. We're going to focus on temperature as a measure of the kinetic energy of the particles. So if we increase the temperature, they're going to have more kinetic energy. Or we could say if they have more kinetic energy, the temperature has gone up. And the more kinetic energy they have, the more they are moving, the faster their velocity. Because if you're talking about one particular gas, its mass won't change. So to have more kinetic energy means it has to be moving at a higher speed or a faster velocity. We'll use the term compression to reduce the empty space between the particles, and expansion means to increase the space between the particles. So really when we talk about gases, it's not so much the particles themselves, but the amount of space that they take up. Okay, now we said earlier that gases easily move past each other and that there are no significant forces of attraction. Well, we have two new vocabulary words that we need to look at. The first is diffusion, and diffusion is the movement of one material through another. So basically in terms of gases, it's gas particles moving from a confined space out into an open space. And then effusion is a gas escaping through a tiny opening in a container. So the idea for effusion is, if you think about the last time you went to a birthday party and you brought home a balloon, and you kept that balloon, and over time it got smaller and smaller and smaller until it just kind of deflated. Well, what's happening is the helium atoms in the balloon were actually escaping through tiny openings in the material that the balloon was made out of. So you might have noticed Mylar balloons stay inflated longer than latex balloons. That's based on the material that they're made out of. The Mylar has less of those tiny openings to let the gases effuse out of the balloon. Now, to compare the rates of effusion, we need to look at Graham's law. And Graham's law of effusion states that the rate of effusion for a gas is inversely proportional to the square root of its molar mass. Okay, what does that all mean? Well, here's what it means. If a gas has a very small mass, okay, so very small gas atoms or gas molecules, they're going to effuse at a faster rate. If a gas has a really big mass, it will effuse at a slower rate. So they're inversely proportional to each other. So let's look at an example of this. Okay, ammonia, which is NH3, it's a gas, has a molar mass of 17 grams per mole. Hydrogen chloride has a molar mass of 36.5 grams per mole. Which one will effuse faster? Well, Graham's law says that the smaller the mass, the faster it effuses. So in this case, which one has the smaller mass? Ammonia does. That means it will effuse faster than hydrogen chloride. So if you filled balloons with both of these gases, the balloon with ammonia in it will deflate faster than the balloon with hydrogen chloride in it. Okay, one major component of this chapter is going to be gas pressure. And pressure is defined as a force per unit area. Okay, now when we're talking about gas pressure, we're basically talking about the gas particles colliding with the walls of their container. That's what gas pressure is. So this sentence right here, gas particles exert pressure when they collide with the walls of their container. That's what we have to focus on, okay? If we can increase the number of collisions, the gas will exert more pressure. If we decrease the number of collisions, the gas will exert less pressure. And there are different ways we can make the number of collisions change. We could change temperature, we could change volume, we can change the number of moles of particles. But all of gas pressure has to do with the number of collisions of particles with the walls of their container. Now there are a bunch of different units for pressure, just like there are a bunch of different units for mass and for volume. We are going to use the atmosphere as our main unit of pressure, and there are a couple of conversion factors that are given here that you need to be able to convert from other units into atmospheres. And one of those is the kilopascal, or kPa. So it says here that 101.3 kilopascals, or kPa, is equivalent to 1 atmosphere. And we're going to use ATM to abbreviate atmosphere. So if we want to make that a conversion factor, if I can get my pen here to work, then we could say that 1 atmosphere is equal to 101.3 kPa. Here we go. So 1 atmosphere is equal to 101.3 kilopascals. And as always, with any other conversion factor, we could flip that over if we needed to. Okay. Now we're also going to look at these two right here, millimeters of mercury and torr. Both of those are the same thing. So 1 atmosphere is equal to 760 millimeters of mercury, and 1 atmosphere is equal to 760 torr. So if you are given one of these other units and you need to convert to atmospheres, these are the conversion factors you would use. Okay, we're not really going to look much at PSI, we're not going to look at bars, those are American systems. We're going to look at the metric units, which are the atmospheres and the kilopascals for the most part. Okay, we have one more part we need to look at before we go to the next video, and that is Dalton's law of partial pressure. Now when we talk about partial pressure, basically what that means is when you have a bunch of gases mixed together, for example air has a bunch of gases mixed together, the individual pressure of the individual gases all contribute to the total pressure of the mixture of gases. So if we know, for example, in air, if we know the partial pressure of nitrogen and oxygen and carbon dioxide and water vapor and argon and all the things that are mixed together, we could add up all those partial pressures, and that would give us the total pressure of air. Okay, so and this only applies to a mixture of gases. Okay, so if it's a pure gas, this doesn't apply. There's just one pressure. But if it's a mixture of gases, then this is the law that you want to use. So let's look at our example. It says a mixture of oxygen, carbon dioxide, and nitrogen has a total pressure of 0.97 atmospheres. We want to know what is the partial pressure of oxygen if the partial pressure of CO2 is 0.70 atmospheres and the partial pressure of N2 is 0.12 atmospheres. Okay, so here's our formula. So our total pressure is equal to the partial pressure of oxygen plus the partial pressure of carbon dioxide plus the partial pressure of nitrogen. Okay, so what do we know? Well, it tells us that the total pressure is 0.97 atmospheres. Okay, we want to try to find the partial pressure of oxygen. The partial pressure of CO2 is 0.70 atmospheres, and the partial pressure of N2 is 0.12 atmospheres. So, how do you solve for the partial pressure of oxygen? You subtract. It is that simple when you're dealing with Dalton's law of partial pressure. It is just subtraction. So if we solve for the partial pressure of O2, we would get 0.15 atmospheres. There we go. That's the answer to the question.